Hello, everyone, and welcome to our seminar series on resilience of autonomous systems. It's a great pleasure for me to introduce today's speaker, Dr. Yang Lu. Yang is a lecturer at the Systems Security Group in the School of Computing and Communications at Lancaster University. He holds a PhD degree in electrical engineering from Pennsylvania State University, where he worked as a postdoctoral student as well after completing his PhD. He also worked as a PhD intern at the Pacific Northwest National Laboratory as a visiting scholar at Georgia Institute of Technology. And his research interests are focusing on cyber physical privacy and security, distributed control and optimization of multi-agent networks, and machine learning. And his presentation today will be primarily on these last couple of research topics. And the title of the talk is Resilient Federated Learning, where performance meets constraints. So Yang confirmed that he would be happy to receive questions during the talk, should you have questions, and there will also be time for questions at the end of the presentation. So Yang, the floor is yours.
Okay, thank you, Radu, for the introduction, and thanks everyone for attending today's seminar talk. Today's my talk is resilient federated learning, where performance meets constraints. I will start with just reviewing very basic things of traditional multi-agent machine learning. I think people are very familiar with this kind of architecture of multi-agent machine learning. Usually you may have a central server here, and you may also have a bunch of users or learners or agents. I will use different terminologies interchangeably in the talk. And each learner will upload the data, its data set, to the central server. And the server will perform some whatever learning algorithm to train a model and send the model back to all the users. So in this traditional paradigm, there are two potential issues. The first one is potential leakage of the user's local data sets. Usually the data set could be confidential, could include secret information of the users. And secondly, it may put too much burden on the server side, because all the machine learning computations are on the server side. If you're running the deep learning algorithm, that could be too much for the server. But it depends. Sometimes if you have a superior server, then it is not a problem. But in certain cases, it might be an issue. So to mitigate these two potential issues, people proposed this federated learning technology. We still have a very similar architecture here. We have a central server and we have a bunch of users. The key difference is that now, instead of directly sending data to the server, each user will first locally train a model over its local data set, and then each user will upload the model to the server. And when the server collects all the local models from the users, the server will perform an aggregation of the local models to obtain a global model and send the global model back to all the users. So you see that in this way, only the local models are transmitted over the communication channels, while the raw data never leave the learner's devices. So somewhat it is kind of privacy by design. Local data sets never leave their owner's devices. It enhances the privacy issue. And also the learning task is distributed at the user side. The server only performs some kind of aggregation, which is quite lightweight usually. So we can mitigate these two issues. And due to these two major advantages, federated learning has been applied to many problems. for example, intelligent transportation systems, smart buildings, multi-robot systems, smart grids. I'll just give you a few examples, and like actually a lot of other applications also. But there are still some open challenges we have to address for federated learning to be used to broader applications, especially some cyber-physical systems. If you have a cyber layer and not a physical layer, we may have different new constraints. For example, the first set of constraints happened in a local data set. I use these icons with different shapes and colors to indicate that the data set could be very different, heterogeneous, than if we only train a single global model that could not meet different users' requirements. We will talk about on these constraints later on more specifically. And the second constraint happens along the communication links. Although it can somewhat resist, enhanced privacy, but it is still possible. Attackers can learn something from the local models. And also there could be active attackers who can, tamper the models transmitted over the lines. So we have attacks over the communication channels if the channels are open and insecure. And the third potential constraint is that the traditional federated learning requires a fixed central server. However, in some cases, the central server may not be fixed. You may not have a stable fixed central server. They may be moving. And also in some other cases, you may not even have one entity which is connected to all other entities. So we have these constraints from different applications. So in this talk, I will introduce 3 of my recent works, which attempt to address these limitations. The first one is about adaptive federated meta-learning. So here we just review again the first set of constraints mainly. So we see the constraints on limitations on data side. Basically, data in different users or different edge nodes, they may be highly heterogeneous, have non-ID distributions. They may be highly dynamic if you are having a highly mobile environment. And also, some users may have very limited data size, right? And under these constraints, by the current learning scheme, the server will just train a single common global model and distributes the model to all the users. So in this case, it cannot, adapt to different user requirements. For example, if a user has very limited data size, then this user may want to, more learn from other people's data to have better generalization. However, if one user has relatively adequate data, this user may want to more focus on its own data or similar tasks. So it requires us to provide maybe personalized global models. And also the current scheme, as mentioned, it relies on a fixed central server, which might be problematic. You may not have such a stable fixed central server. And in this work to address these issues, we have these overall objectives. We want to propose an adaptive and hierarchical federated meta-learning framework. Specifically, we will adaptively match characteristics of heterogeneous and dynamic data. We will do this by dynamically generating data clusters, and we will train personalized models for different users. We do this by generating multiple hierarchical learning loops. And finally, we will remove reliance on a fixed central server, and we do this by dynamically picking edge nodes to serve as a central server. So this work is based on the paper here. And so first, to deal with heterogeneous data, we will partition the user's data into different clusters based on their representation vectors. We use variational autoencoders, which is an unsupervised learning model. It takes in users' data and then extracts a representation vector here, which is can represent the user's data set. Then we use this vector, and then we use k-means to perform an unsupervised k-means-based clustering, so that very effectively we can partition different users into different clusters based on the features of their representation data, or representation vectors. And after that, we have several clusters now. And to really enhance this adaptivity, we further introduce this hierarchical meta-learning architecture now. So you see here in this picture, we have this several clusters now. Each cluster consists of several users which have similar features, similar tasks, or similar data, right? And we have three loops. The first loop, we call it inner loop. Basically, just the user's local training problem. It just learns a local model by its local training data set. And then we have an outer loop. This outer loop is the cluster level meta-learning. It aims to extract common features from similar tasks inside a cluster and optimizes adaptability of similar tasks. And then, so basically, we have a cluster level aggregation. And then we have a global loop, which just another outer more. It's another global level aggregation over the cluster level meta models. It tries to extract global knowledge across different tasks, different clusters. So this optimizes generalizability across heterogeneous tasks. And to really, accelerate the adaptability and try to meet different users' requirements, the key idea is to pick a suitable initial training model for each user's local training. In traditional federated learning, each user's local model usually uses the global model in the last training round, right? And here we use a mixture of a user's own local model and the cluster level meta model and the global level meta model as the initialized model in each training round. So if a user wants to more emphasize on its own task, it can assign a higher weight on its own local model. And if the user wants to, maximize adaptability of similar tasks, it can assign a larger weight on its cluster level meta model. Otherwise, if the user wants to maximize generalizability, then the user can assign a larger weight on the global level meta model. So depending on users' data size or some other considerations. So it provides some flexibility in this overall training process. And of course, you can, if you take a look at this figure, you can even have more layers, more than 3 layers, if you have more specific considerations, subclusters. But this provides you a very natural way to do this partitions, these layers, 3 layers. And as mentioned, the users may be of high mobility, so their data set could arrive in stream dynamically. So instead of having a fixed cluster, fixed layers, we will dynamically perform this clustering and the learning loops, right? So based on the instant data features. And also we will dynamically pick the central cluster level as well as global level central servers by just picking the current available users in the network to address this, so that we can avoid this potential issue of fixed central server. And we perform some experiments to validate the performance of the proposed design. We use a multi-exercise edge computing environment with from 5 to 100 edge nodes. and we use 3 workstations. We test on 3 data sets, MNIST, Cipher10, and some synthetic data sets we created. And we tested on FNN, feed-forward neural network, CNN, and this CMRL, these 3 different types of deep neural networks. So this is the performance for classification tasks. So here in this results, we have one parameter gamma, which controls the heterogeneity levels of the data set. With a larger gamma, it means that the data features among users are more different. So we compare to 2 baselines. The PPFM, the green one, is our algorithm. The blue one is per average algorithm, and the red one is the fed average algorithm. These are 2 baselines here. And we can see that for different cases of heterogeneity levels, our algorithm can achieve better performance in terms of accuracy. And it is the results for regression. Similarly, we compare to these 2 algorithms, and we have an additional line, which is black one. It is the oracle, basically the ground truth. So all the users now try to perform some regression to fit sinusoidal functions with different amplitudes and phases. So again, we show the mean squared errors, and our algorithm achieves lowest mean squared errors compared to the other 2 baselines. So okay, so basically that's the first work trying to address the heterogeneity issue over data. And now the second work, secure federated meta-learning. So this one is developed, based on the first work. We built the model based on the hierarchical layered meta-learning, federated meta-learning. But here in this work, we consider a different problem, which is security. So you may have data, you may have active attacks like data poisoning attacks. You may have model poisoning attacks, and you may have attacks on parameters, right? When the users upload their models to the central server, the model could be changed, tampered by external attackers, or even the internal users could be corrupted. This work is based on the conference paper here. So to address this problem, we developed a kind of framework which has 3 parts to enhance the security overall. The first part is just the federated meta-learning I introduced. So we call this robust by design framework. Because in this framework, we partition all the users into different clusters. So we make the problem more distributed now. So the thing is that, for example, even if one cluster is completely corrupted, if you know, okay, then you can just completely remove this cluster, and it will not affect the remaining clusters. So by making the learning problem more distributed, usually it is more robust. So we call this robust by design. And the second block is this detection phase. And in this part, we have 2 detectors. One is kind of an offline raw detector, which is rule-based. We will introduce this one later in more details. And another one is a variational autoencoder-based detector. It's an online, final grade detector. So by running these 2 detectors, we will remove some attackers. We will detect and remove some detectors from the learning process. And then we go to the third phase. So this is with the remaining users in the learning process. We will perform the global model aggregation, but we will still perform a robust model aggregation to try to further mitigate the impact of attackers. So that is the overall design. So we have introduced the first part. So we will start with introducing these 2 detectors in the second part. The first one is the residual rule-based detector. So to build this detector, the users will upload their local models to a central server, and the central server will put all the local models into such a model matrix. For example, here we have n users, and each user's local model is p-dimensional. So it's theta 1 to theta p is just the parameters of this local model. And we put them in this way. And then we will just rank each row from the smallest to the largest, just rank them. Then we have this ranking matrix. Then we will use these k-means to do unsupervised learning, so that we can, based on these ranking matrix rows, we can detect which rows are far away from majority of the rows, majority of the local models, and it indicates that those rows, those vectors which are far away from the majority could be adversarial, and we will remove these users' local models from the learning process. And this rule-based detector is very lightweight. It's just some ranking matrix operation, k-means operation, so we can form this one offline and provide a raw detection. And after this detection phase, we remove some of the attackers. We will have somewhat, sanitized users. Then we will apply another detector, variational autoencoder based one. So here again, the VAE will take the data side of each user as input, and then generates latent vector Z here. And we make use of this latent vector, and we can calculate. I will skip the details. We can just calculate two scores here. One is reconstruction error, one is similarity of latent vector, just by using the latent vectors from VAE. Then we take these scores simultaneously, and then if some users' latent vector has a very large score, which is maybe larger than some threshold, then we treat them as adversarial, and we will remove this user from the learning process. So this one provides a finer grained detection. So after the detection phase, we will perform this global model aggregation over the remaining users in the network now. And here you see that so this omega basically is the global user's local model, and we aggregate over the user's local models, and we have the mean here. For example, this point is the mean, and then some users' models are far away from the mean, and some are near to this mean. And now we're not going to remove anyone now, but we will allocate a smaller weight to those ones whose models are far away from the mean, basically to provide some more robustness in the process. So we call this similarity-based global model aggregation. So based on how similar you are to the mean. So we have these three phases of the robust design. And then we perform experiments to validate the performance. Again, we have similar environment, we have similar data sets and learning models. So this is the experiment result. We compare to this green curve is the no attack one, basically that is the best we can achieve. The blue one is our algorithm. The fed average one is basically the fed average means that the algorithm performs multiple batches in each round of learning, and instead of uploading gradient, it uploads parameters. And geometric median method, instead of using all the users' local models to perform aggregation, geometric median method just use the geometric median of all the users' local models. So it provides some robustness. And the crumb method, it uses also only one local model, which is nearest to most of the local models. So also provides some robustness. And the last one is no defense, basically could be the worst possible performance. So we can see that for both MNIST and CIFAR 10 datasets, our method achieve a much better, in some cases, much better performance in terms of accuracy than other algorithms. So here, mostly it is because our method has two parts of detection phases. Robust phases. We first detect and remove attackers, and then we still have robust design. So in our algorithm, it is kind of resistant to the number of attackers. Even if you have many attackers, because we have two detections before the robust aggregation part, we are able to remove the majority of the attackers. But in contrary, for example, the geometric median one, if you have too many attackers there, without a detection and removing part, they just perform this robust aggregation by taking the geometric median. But if you have too many attackers, then the median could be very, very poor quality. So this is one major advantage of our algorithm. Right. So, okay. And then I'm going to keep talking about the third one, privacy preserving decentralized federated learning. So this work, we will try to address the privacy issue and also the central server issue. So here, as mentioned, even if federated learning can somewhat enhance privacy, but it has been pointed out that it is still possible attackers can extract some information, a data set from the local models by some model inference attacks. And also, this centralized aggregation problem, it depends on a central server, which may not exist at all. And also, it suffers from single point failure, right? And this work is based on the journal paper here. So I've tried, we first motivate a little bit of this peer-to-peer framework. In this work, we will study peer-to-peer decentralized communication topology framework. For example, in power systems, usually, for example, load forecasting of distributed energy resources is a problem. We have a lot of users like power consumers or generators. They are geographically distributed over a large area, and there is no single central server which is connected to all the users. And also these vehicular ad hoc networks. So these vehicles are also distributed along some area, and they just use this network to communicate with each other without necessarily having a central server. And since they are in a highly mobile environment, they have limited communication range and capability. So you may not have, at least you may not have a stable central server. So our objectives here, we want to achieve federated learning over a decentralized, which means completely peer-to-peer framework, communication topology like this. You do not have a central server here. And also we want to ensure privacy. Theoretically, we can ensure privacy of users' local models. We want that the model aggregation process does not leak any information of benign users' local models. And how do we achieve the first objective, which is peer-to-peer global model aggregation? We use the average consensus protocol algorithm. So here you see that this is the update rule. So this theta, this k here, k is the time instant. K is the time instant, and theta jk is the local model. Theta j0 is the local model of learner j, and theta jk is J's local model at case iteration of consensus. So in the communication network, all the users will just exchange their local models to their neighbors and then perform this update rule to update their local models. And if the weights AII, AIJ here are properly chosen, we can ensure this asymptotic convergence. Basically, all the users' local models will finally asymptotically converge to the average of all the users' initial models, which is basically the global model. So how do we construct such weights to guarantee convergence? And especially when we consider time-varying communication topology, your neighbors could change and they could leave and they could join. We use this image method. So you see that basically, if I and j are neighbors, and aij is just 1 over this ni and nj are neighbors of I and j respectively, and we compute these weights in this way. So this kind of weights update is also purely peer-to-peer, do not need network-wide information. For example, if you have this very simple structure for users here, by using this image method, so this is corresponding matrix of aij. So we can do that. In this way, we achieve this peer-to-peer global model aggregation. Then we still have to secure this update rule, because now you are still directly exchanging the local models, and it still suffer from model inference attacks. And to do that, we integrate secret sharing. And first, I've introduced the idea. So the idea is each user I would like to use a new state I0 instead of the true local model as the initial state for the consensus protocol. But we need to guarantee correctness and privacy. Correctness means that under this new initial models, initial states, the average consensus will still reach the correct consensus value, which is the global model. And privacy means that the observation and derivation process of these new states, new initial states, do not disclose any information of users' true local models. So we have these two objectives. Now, how do we obtain these proper new states? So we use this Schama secret sharing scheme. So I've just very briefly introduced the idea behind this scheme. So Schama secret sharing, it allows to split a secret, because the secret C into n parts. So use polynomials to generate shares. For example, your C is the secret, and say if we have 6 people here. So and maybe we know that at most 3 of them, T3, at most 3 of them are attackers, but we do not know which 3 are attackers, but we know the bound. At most 3 of them are attackers. And now we try to split this secret C into 6 shares. Each person will have 1 share. Then we can use a polynomial of degree 2, just a degree 1 less than this T value, degree 2. And we randomly choose 2 parameters, two coefficients A and B of this polynomial, and the constant term is just our secret C. Then we will plug in 1, 2, 3, 4 till 6, just plug in evaluated function at 1, 2, 3, 4 till 6, and we have 6 numbers. These are just the 6 shares of our secret C. Then distribute 1 share to 1 person, right? And then property, we have this reconstruction property which guarantees correctness. Basically, any subset of T or more shares can reconstruct the secret C. And also privacy, any subset of T minus 1 or less has no information of the secret C. Basically, it is because we are generating the shares by using a polynomial of degree 2. Now we know that any three or more points, we can reconstruct this polynomial. Like if you are using a line which is degree 1, then if you have any 2 points or more points on the line, you can uniquely reconstruct this line. However, if you only have 1 point, if it's a line, then there's no information which line it is, right? So that is the reconstruction and privacy properties, the intuition of these two properties. And this is what secret sharing can guarantee to us. So we use this technique to enhance privacy in our global model aggregation. So basically, secure distribution of theta I, we will generate shares of each user's local model theta I0, and then distribute the shares of this theta I0 to the user I's neighbors. Okay, so for example, user I will just apply secret sharing to generate a polynomial of degree. This is number of neighbors, degree ni, and then distributes the shares to all its neighbors and also to itself. So you see that the degree is the number of its neighbors. So we need at least ni plus 1 shares to reconstruct the theta I0. And if any less than ni plus 1 number of shares cannot reconstruct, does not include any information. And consensus iteration, all the users will sum up all the shares it received from its neighbors, and then use this as a new initial state of the consensus protocol. And then they will just run this normal consensus protocol iteratively. And we can guarantee by the reconstruction property of secret sharing, finally, all the shares will be summed up together, and also by this convergence property of consensus. So we can guarantee that finally we can still achieve the correct convergence converge to the correct global model. So this is correctness, and also privacy. For individual users, user I's local model is protected if and only if at least one of its neighbors is benign. We can theoretically prove all these properties. And network-wide privacy. So we say perfect privacy is achieved if and only if there is no proper subset of benign users that are completely surrounded by attackers. We say perfect secrecy, which means we even do not allow disclose of partial sums of partial users. That is also maybe some kind of privacy leakage. So these are theoretically guaranteed by making use of secret sharing properties and also average consensus properties. And so this is more of a proof of concept simulation. It's not those empirical works. It's more of a theoretical work. So we have this simulation environment. We just use a Lenovo laptop, and we test on the MNIST dataset, and we use variation autoencoder for users' local training. And this is the first result. We test on just to show the convergence of consensus process. We see all the users' curves, they converge to to the same value, which is the correct global model value. Yeah, actually, we have some other results, simulation results, to even show the correct performance under time varying communication topologies, and also we investigated the impact of different communication topologies. Yeah, but I did not include those figures in this slides. And and this talk all these works are partially supported by the TASENS project. Okay, that's it. I think we have enough time for questions.
Thank you very much, Yang. This is a very interesting talk. So I think I'll open the floor for discussions and questions now. If there are any questions, you want to raise your hand. Alan?
Hi, yes, thank you. That was a really interesting talk. I've always had a bit of a fascination with federated learning, but I really don't know too much about it. So apologies if this seems like a really naive and unfortunately probably very dull question. So with regards to, I guess, the last and the first part of this talk, in particular more to do with the first part when you talk about adaptive federated learning, I'm sort of, again, I apologize. It's such a dull question, this, but I'm sort of intrigued when it comes to scaling this sort of approach, right? With more models, more data sets and all that, more complicated data sets. But I suppose it's not just that. The thing I'm sort of intrigued about more specifically is, let's say you have this wonderful set of models and you do this, and now I want to take in a brand new model and put it in. I'm sort of intrigued with all the interactions that are happening between the inner, outer, and the global sort of clusters. How much retraining would you actually have to do if I wanted to bring something new into this? Or do you think a lot of them are still isolated enough that it doesn't require, I suppose, a full ground up retraining of everything?
That is actually a very nice question. Yeah, if you have some new person join in, you do not necessarily want to redo everything. Although we are dynamically generating clusters and loops, but there is always a trade-off. We may generate new clusters and loops maybe every 10 training rounds or every even more training rounds, depending on the situation. If one new person coming in, usually we just take the latent vector of this person and allocate this guy to some of the existing clusters now, without really redoing the clustering operations in here. And then we will just include this guy into one of the clusters and do the model training. And maybe, right, if you have even more new people coming in, then then we can, if we find it necessary, now we have to do a reclustering operation, then we'll do that. So there is a trade-off here in terms of performance and complexity.
Right, Grisel?
Yeah, thank you so much for the talk. It is really interesting and lots of new concepts that I had to review much more in detail after the talk. I have one question regarding how much does it increase in the computational resources when you're having all these interlinked types of robust techniques in comparison, for instance, in the graphs you were showing compared to some mean algorithm. So I suppose computing this algorithm would be much quicker than passing through all of these robustness techniques. But again, maybe I'm wrong, but are these all done in the design stage rather than when it's deployed?
I mean the second part, the robust.
A little before there was some graphs comparing with other algorithms.
This one?
Yes, that one.
You say the complexity around the running time or something.
Yeah, so I was wondering if it takes much more computational resources to do the
inevitably that will be more depending on the scale of the problem, mainly because we have this we have this part, this VAE based deep neural network based detection. And if you're running this for example geomet method or cram method, is just to pick the median or one vector without running any deep learning method for detection, that would be super fast. And again, so basically we provide another probability of flexibility. So if you really have limited resources, right, then you can something you can do is you can just only run this rule-based detection. So this is very lightweight, no deep learning things there. Or you can still run this one and this one, sequentially, but you may allocate a most conservative threshold in the first part, try to remove more attackers in this part. This one you can assign us, a conservative threshold, so that here you only have maybe relatively fewer learners remained, but provides you a flexibility in this way.
Okay, just a small comment. These two steps are also happening at runtime? or just at design time and then the synthesis of the.
So this is the BAE is kind of running time, but basically
Okay.
if you have this dynamic online data coming in, yeah.
Okay, thank you.
Thanks.
Jinwei?
Yeah, hi, thank you for the nice talk. And I apologize as I cannot make my camera working today for some reason.
Worries.
So your work has shown great potential in enhancing privacy and detecting anomalies, but primarily based on for the distributed system. So given this context, I just wonder, do you think that an individual robot could benefit from your findings, especially in predicting unexpected changes during its runtime? So for instance, do you think it's possible to segment the operational timeline into intervals and treating each as an entity for analysis? So just want to hear your thoughts.
I may not completely understand. If you're talking about single robot, you're saying segment timeline into different intervals, right?
Yeah, and we treat each intervals as a distributor, as a single entity for analysis in the similar way as you do here.
Okay, treat different intervals as maybe different entities. Now we still use this distributed framework, right?
Yeah.
To do that. That is definitely very interesting idea. So which limitation you're mainly considering? Privacy, security, or data heterogeneity, or things?
Well, really, we're interested in all type of things. I would just want to see whether because we have slightly different problem, but your solution has a promising result for demonstrating those aspects. I just wonder whether we can formulate our problem in a way that your solution is applicable.
I'm not sure, to be honest, depending on how you segment the problem. And I guess there might be time dependence or dependence on something. So if we can treat them, I'm not sure, independently, like privacy, because I'm doing this peer-to-peer privacy here. I think we definitely have to look into the dependency here. Like sometimes in the system, if you have this time sequence, then the privacy, single, one-shot privacy is not enough. I'm just, so I think that is more complicated. I do not have, really good answer for that question, for this question. But
yeah, all right, no worries.
Yeah, I mean, it's very, very, inspiring question. I think I never think about this problem in this point of view. It's very different to model the problem, decompose the time sequence, right? But to treat it as a distributed system.
Yeah, because your solution has a promising result, but it's only mainly for distributed system, and we have interesting more time series temporal related problem. So we yeah, all right, no worries. Thank you.
Yeah, thanks for this very, very interesting question. I mean, we can discuss later if you're interested in that.
Yeah, sure.
Yeah.
Right. Any other questions? Please, Carlo.
Sort of following on a little bit from Jingwei's question in a way. So one of the things is, so I come from a robotics swarm intelligence sort of background. So when I saw a lot of the work that you were describing here in terms of distributed systems, I couldn't help with that part of my brain kind of like tinkling a little bit and see there might be some potential overlap. But I think in one sort of strand, I was sort of curious to hear your thoughts on is there's quite a bit of work in swarm robotics or swarm intelligence regarding what if you had a few of these distributed agents that are malicious attackers, right? How can we stop them from influencing the rest of the swarm from doing the wrong thing, essentially? And what's kind of interesting in these kind of works is because there's usually an additional component to it, i.e. being like a physical agent, it's also how do you act upon the world given this? So at the moment, from what I've seen in the work, in particular when you were describing the sort of secure federated learning section of this talk, it seems like a lot of it is to do with filtering out data.
Yeah.
And then your learned agents, your learned components are behaving as they normally would. But let's say, for example, and maybe this doesn't actually happen, it's just a hypothetical, but let's say there's some sort of shift in distribution, like the attackers have changed, the attackers have learned on how to maybe come across slightly differently. So now your VAE encoder might not necessarily hatch onto that, right? They might seem a bit too similar and you might have to relearn it. So I was sort of curious of, if given these sort of things could happen, is filtering data enough, or do you think there needs to be an additional aspect in terms of the actual acting upon it, I suppose, or having your agents, even if you think I might trust everybody, but perhaps I should be more conservative in whatever prediction I give, or whatever action I decide to enact upon the environment or the world or something like that?
Okay, yeah, very, very interesting question. But actually, something I'm also working on now. So this distribution shift to online learning over streaming data in the presence of potential distribution shift. I'm replacing deep neural networks now. I'm not using VAE, right? I'm using non-parametric models, maybe like Gaussian processor or some other processes. Basically, they could be, more time consuming to do the computation, but they can provide you fast adaptation to new observations, to new distributions. So they have been widely used in online exploration, like reinforcement learning is non-parametric models. So I'm trying to apply non-parametric models to federated learning, online federated learning. So that provide us a way so that it's based on the instant data samples, even just 1 or 2 data samples which significantly change the distributions. Then you can quickly reflect such change, in your problem. And I'm also trying to use some other distributions to replace, popular Gaussian distributions to remove impact from outliers. Because if you think about the online learning over streaming data, if you have outliers, that might be very difficult to distinguish that outliers from attackers, and also the outliers could very negatively impact your learning process. I'm trying to use some different distributions which have this so-called heavy tail effect, which they can better remove the impact from outliers. So that is one thing I'm trying to do to consider this distribution shift thing.
But I guess you're still focusing on the data filtering aspect rather than, right, yeah, okay, perfect. Thank you.
Right, I think we have time for one final question, Grisel.
Thank you. I think it's more like a comment rather than a question, but have you looked into the Isaac James simulator, where there are like multiple robots evolving at the same time in the simulator are policies? So I think following Xinwei question on how to use this for a single robot, for example, maybe this type of simulations could be interesting to look as a case study.
Yeah, to be honest, I'm very interested in this potential idea, to explore its potential ideas. It sounds, really innovative. I'm not sure whether there are any such works in the literature. I don't know. And also the problems mentioned by Callum and you on these distribution shift things, and all kind of open challenge in this area. Yeah, and this experimental works, if we can do something together there, it would be very, very exciting.
Yeah, definitely. Thank you.
Yeah. Thanks.
Right. Well, thank you very much, everyone, for participating in the discussion and asking these questions. And most of all, thank you, Yang, for the very interesting presentation.
Thank you, Radu. Thanks very much. I really enjoy these communications with people. I really got all these inspiring questions, and yeah.